Reciprocal functions. So before we look at the reciprocal functions, let's just work with some reciprocals of some fractions. In this case, some radical fractions. If I want to do the reciprocal of this, I'm just going to flip it upside down. And typically I can just leave it like this. However, we can rationalize the denominator. And we're going to rationalize the denominator here by multiplying that binomial with its conjugate. And when I multiply that by this conjugate, I end up with this expression, 2 times square root 5 minus 1 all over 5 minus 1. So we get 2 root 5 minus 1 over 4. That will simplify to root 5 minus 1 over 2. And this is the golden ratio. And as a decimal value, this is equal to, I'm just going to highlight this, this is equal to 1.618 ... And this value here is equal to 0.618 ... And the decimal parts of these are exactly the same. And so part B, we really know what the answer is already. We know that this is the reciprocal of this value here. It's called phi. This is called big phi. And there's actually a symbol for this. Looks like that. And this is little phi. And that little phi has a symbol that looks like this. And so this is the reciprocal of this same phi value, then is just going to be that value. And we can work out all the radical algebra to do that, but these are mutually reciprocals of each other. So that's the one thing that we can state here. For example 2, we know that they are the A and B are their reciprocals of each other. Okay, so for this one here, we're going to start with the function y equals 2x minus 4. So we have a y-intercept at 4, and we have a slope of 2, so it crosses the x-axis there. So if I just sketch in my graph here, there's my original graph. There's my linear function. And at x equals 0, x equals 0, y equals -4. At 1, -2. At 2, it's equal to 0. At 3, it's equal to 2. And at 4, it's equal to 4, etc. And when we write the reciprocal function is going to look like this. Y equals 1 over 2x minus 4. So we put it all over 1. And then we can make a table of values for this reciprocal function. But now that we've put this into this form, we do have a denominator, and we have to worry about restrictions. And in fact, the restrictions in this case would be x is not equal to +2. Because we're going to end up with dividing by 0. So this is, at 0, we have not applicable. We cannot do this. We actually call this undefined. Okay, so this relates to our rational functions where we divide it by 0. Okay, so we have an undefined value there. And so what's happening is then, if I take the reciprocal values, 1 over -1/4, -1/2, +1/2, +1/4. And what ends up happening then is this graph, at that undefined value, we're going to have a vertical asymptote. This is a key feature here. And so when we have, I'm just going to maybe highlight that, when the original function crosses 0, because that 0 now is in the denominator, that becomes an undefined value and becomes our vertical asymptote. And then we can draw the rest of the graph here. We know that at x equals 0, we end up with -1/4, -1/2, and as it approaches, as x gets bigger, so as this moves away from the x-axis, the graph is going to get towards x-axis because it's going to get smaller and smaller, and then the opposite happens here. So as this graph goes towards the x-axis, the reciprocal graph is going to move away from the x-axis. So it works in a reciprocal relationship. And then the same thing happens over here. We end up with 1/2, 1/4. This is tending towards 0. And note that it's tending towards 0 from the positive side. This is tending towards 0 from the negative side. And then this is going to go up towards positive infinity, because as the y values of the original graph gets close to 0, the y values of the reciprocal graph are going to shoot off to infinity. Okay, and one thing to notice that if we take a reciprocal of a negative, it does not change positive, it just stays negative. So everything on the negative side stays below the x-axis. Everything on the positive side stays above the x-axis. And we have an asymptote along 0, because as x gets really, really big, the f of x is going to get bigger and bigger and bigger, and then that's going to make this divide by a bigger and bigger number, which means we're talking about getting closer and closer to 0. So as a limit, the limit as x goes to infinity or negative infinity, 1 over f of x is going to tend towards 0.